Hey there, I wanted to talk to you guys about something called KSP today. I'm going to talk to you today about something called KSP. If you look at our learning targets, we're talking about this target here, which is I can define a KSP and write the KSP expression. I can calculate it, and then I can also do a calculation of the concentration if I know KSP. So, question, if you find your solubility chart from last chapter, is lead 2 chromate soluble in water? So we would look at chromates right here, and for us, we would say, oh, insoluble. So we would say, you know, lead chromate is going to be a solid or a precipitate. So, this solubility chart is based on something being soluble means that 1 gram of it will, at least will dissolve per 100 grams of water. So if it's considered aqueous or soluble on the chart that we used last chapter, then we're just saying that 1 gram at least of it will dissolve per 100 grams. But even something that comes up as being insoluble does slightly dissolve. So, like I said, even though it comes up as being insoluble, the lead 2 chromate will, to some extent, dissolve. So we would want to think of it like, you know, the lead 2 chromate. And this would be the solid, and then we know that it can break down into the lead ions and the chromate ions. So we are dissociating it. These would be aqueous, so even though it comes up as being insoluble, there are a small amount of ions that will form. This is a process that will happen at equilibrium. It's a dynamic equilibrium, it's reversible, so the lead ions and the chromate ions can find each other and reform lead 2 chromate, the solid. Solid, to some extent, will break up into the ions. So if we were to write a KQ expression for this, we would write it like we write any KQ, where we write the concentration of the products. So it would be my lead plus 2 ions times my chromate ions. And if there were any coefficients, like if there were 2 here, then I would have squared it. And then we would divide that normally by the reactant, but the reactant here is a solid, and when we write our KEQ expressions, remember we throw the solids and liquids out because they don't really have a concentration, a molarity. So KSP is really this KQ for something that's very slightly soluble. So a little more about KSP. So we call KSP is called the solubility product constant, and it's just a special KQ for ionic compounds. And these are those ionic compounds that on our solubility table are going to come up as insoluble, but we note they are soluble to some extent. So it will be, like I just showed you in the previous slide, it's going to be the product of the molar concentration. So these are going to be molarity values. And you're going to dissociate the ionic solids. So you'll get a cation and an anion. And then if there, when you dissociate it, if there is a mole, a coefficient in front of the balanced equation, then you will include those there. Otherwise, they are 1s. So KSP, just like KQ, it is valid only at a very specific temperature. And we don't include, just like with KQ, for KSP, we don't include solids and liquids. So this is kind of that solubility equilibrium that I was talking about, just a picture to kind of show you that even though in the lab we would see the lead 2 chromate kind of sitting on the bottom as a precipitate, we would realize that there are still a small amount of lead ions going into solution and chromates going into solution, but then they're also coming out of solution and becoming the solid. So it's just a dynamic equilibrium that can happen. So doing some of these calculations with you. So the first thing, there'll be times where we can just ask you to write the equation and the KSP expression. So for this problem, we would assume that aluminum carbonate is a solid, and then when it becomes aqueous, even slightly, a small amount of aluminum ions will form in water, so aqueous, plus we'll get 3 carbonate ions, and those will also be aqueous. So our KSP expression is going to be the product of the cations, the cation, squared, times the other ion, which is the anion, and in this case it'll be cubed. So the 2 and 3 are coming from the number of moles of each ion that I get. So interpreting KSP values, when you do solve here, we know that KQ kind of tells us whether we're going to have more reactant or more product in a certain reversible reaction. KSP is going to tell you how soluble it is, even though it's not considered a very soluble substance. So the larger the KSP values, the more soluble they are, the more will dissolve, even though it's a very small amount. So here's an example of a problem you might see. This is copper 1 chloride, and what we would want to do here is always write the dissociation. So the copper 1 chloride solid will break into copper +1 ions and chloride ions. And again, remember this is a reversible dynamic equilibrium. We're going to calculate KSP. So what we're going to want to do is we're going to calculate that based on the starting amount. We have 0.0108 grams that will dissolve, so way below that 1 gram that's required for the solubility table for it to come up as being technically soluble, but this small amount will dissolve. And then what we're going to do is we're trying to figure out molarity, so we're trying to get to moles per liter. We know that water has a density of 1, so 1 gram of water equals 1 milliliter. So by doing that, we got rid of our grams, we're in mils. So we're trying to get our milliliters to liters and our grams to moles so that we know the molarity of the copper chloride, and then we can use the mole-mole ratios to get the molarity of the copper ions and the chloride ions. So I would then want to make sure that I am in liters. So I know there's 1,000 milliliters in a liter, so I can cancel. So I'm at this point, I'm in liter, which I need. Now I'm going to get rid of my gram. So I know the molar mass. So 1 mole of copper 1 chloride has a mass of 99.00 grams. So if I look at this, my grams cancel, I'm in moles per liter. So I do have a molarity at this point. And so my answer would be 0.00109 molar. And that would be the concentration of the copper 1 chloride. This would be 0.00109 to start with, which means I'm going to get a molarity of 0.00109 moles per liter of copper 1 ions. and the same 00109 molarity of the chloride ions. So now I can plug into the KSP. So KSP, I would want to write the expression, is going to equal copper ions times the chloride ions. And then remember, we're not going to include the copper 1 chloride because that's a solid. Now I can plug in these two numbers and I can solve and get a value. So when I do that, I'm going to have 00109 and 00109. And remember, just like KQ, there is no unit, so 1.2, 10 to the negative 6. So by knowing that KSP value, I could compare it to something else and then figure out which one is more soluble than the other. Here is another type of problem. So for this problem, they give you the molarity to start with, so it's not as much work as that last one. I would want to take the copper 2 bromide, the solid, dissociate it into the copper ions and the bromide ions. And then I would want to write the KSP expression, which is only going to include the ions and not the solid. So for this one, I'm going to square because there's a 2 in front for the coefficient of the bromide. So I know that I'm going to make 1.09 10 to the negative 3rd molarity of the copper 2 bromide. So because we're in a 1-to-1 mole ratio, I'm also going to get 1.09 times 10 to the negative 3 moles per liter of copper plus 2 ions. And then I would get 2 times that because I have 2 moles here for every 1 mole of the copper 1 bromide, copper 2 bromide, sorry. So it'd be 2 times the 1.09 times 10 to the negative 3. So I would get 2.18 times 10 to the negative 3 for my molarity of bromide ions. So then I can plug in down here. It would be the 1.09 for the copper plus 2 times the 2.18 times 10 to the negative 3rd for the bromide, and then I square it. So I do use the 2. Once I multiply the number of the original molarity times 2, but then I also square it. And when I'm done, I will get an answer of 5.18 times 10 to the negative 9. So no unit. And if you compare that number to the previous, you know that this is less soluble than the previous example. Here's one more type of problem. This is calculating now the molarity. So the others were calculating KSP. This is silver bromide. So again, this solid, to some small extent, will dissociate into the cation and the anion. My KSP expression is going to be just like KQ, products concentration over reactant, but the reactant we're going to throw out because it is a solid. And then I can plug in. So they're telling me the KSP is 5.0, 10 to the negative 13. And then I know that if I have X of this, I also have X of this. So I would have X times X. So 5.0, 10 to the negative 13 is going to equal X squared. I would want to take the square root of both sides, and I would get 7.07, 10 to the negative 7th as my molarity of silver bromide, because this is X. So my concentration of my silver bromide is equal to the concentration of my bromide ions, which equals my silver ion concentration, which is this value.